Forces and moments acting on a spinning mass often cause the mass to move in a counterintuitive manner. This is easily shown with a spinning wheel supported at one end of its axle. The center of mass fails to fall downwards. The axis of the wheel is spinning around the supporting rope. Could we predict in which direction the axis will spin? This video will provide you with tools to make predictions about the behavior of objects with angular momentum under various loading conditions. A mass rotating about an axis has angular momentum. This angular momentum is in a direction defined by the right-hand rule. If it's rotating from the x direction towards the y direction, the angular momentum is in the positive z direction. This is the case no matter how the set of axes are oriented in space. The angular momentum of an object spinning about an axis through its center of mass is equal to the polar moment of inertia of the mass about that axis times the angular velocity of the mass. The angular momentum can be changed in direction or magnitude by applying a moment to the mass. The time rate of change of the angular momentum is equal to the net moment applied to the mass. This equation shows that if there is zero net moment applied to a mass, angular momentum about its center of mass remains constant. If we want to calculate by how much an applied moment will change the angular momentum, we can integrate our original equation. Remember, this applied moment could change the direction of the angular momentum, its magnitude, or both. Let's try this out. Here we have a gyroscope, a rotor suspended within a rotating frame on low friction bearings. These allow the mass to spin at a high angular velocity, whilst only applying a negligible moment to it. Due to its high angular velocity, the rotor possesses a large amount of angular momentum. In this case, the angular momentum is directed towards you. As the external support is rotated in space, the gyroscope maintains its orientation. Because no significant moment is applied, there is no change to the direction or magnitude of the angular momentum of the rotor. You may wonder how angular momentum is affected when the applied moment is not zero. We'll start with an analogous linear scenario. When a mass is moving in a straight line, it has linear momentum, equal to its mass times the velocity of its center of mass. When a force is applied to the mass perpendicular to the direction of travel, the linear momentum changes direction. The magnitude is unchanged. When the force is removed, the linear momentum vector remains constant. Let's look at that again from a reference frame moving along the same path as the car. We can see that the angle alpha is increasing as the mass rotates. If we fix axes to the car, the linear momentum is in the positive y direction and the force is in the negative x direction. The rotation of the momentum vector about the center of mass is in the positive z direction, out of the page. Rotation of the angular momentum vector about the center of mass is caused by the application of a moment perpendicular to the angular momentum vector. The applied moment has a direction given by the right-hand rule. The rotation of the angular momentum vector about the center of mass is known as precession. The direction of precession is also given by the right-hand rule. The angles between these three axes remain the same, regardless of their orientation in space. Therefore, if we know the direction of two axes, say the angular momentum and the applied moment, we can work out the expected direction of precession. You can remember this by using your right hand. These axes are related by this cross product, but you don't need to use it in this course. Let's try this out with an experiment. This is a small boat with a relatively large rotor mounted in it. The waterline is marked, so we can observe any tilting of the boat. First, we apply a moment to the boat when the rotor is stationary. In which direction do you predict the boat will rotate? Pause the video and write this down. Okay, the angular momentum of the rotor is zero, so the precession will also be zero and the boat will not tilt. The direction of rotation will therefore be in the positive z direction, the same as the applied moment. Now, we repeat the experiment, but with the rotor spinning about the spin axis. The angular momentum is significant, so as we apply the moment, there will be some precession causing the boat to tilt. We decide to apply the moment in this direction. We can orient these axes so that the angular momentum and moment axes point in the correct directions. In which direction will the boat tilt due to precession? Pause the video and write this down. We can see that the precession vector is directed to your left, causing the boat to tilt, pushing its right side deeper into the water than its left. Now we apply the moment and observe that this is in fact the case. I will leave you with a question to test yourself. Here is the gyroscope from earlier. If we give it angular momentum in this direction, and apply this moment to it, in which direction will precession cause the spin axis to rotate?